Series parallel circuits.
Yes. Look at that. My age. It's a gold star. All right, so last week we reviewed series circuits and parallel circuits. The things to remember about those is, I think you know all this now, but series. This applies to series circuits, but it also applies to every portion of a bigger circuit that's in series. Same current. So if I have a more involved circuit, everything in series will have exactly the same current. Even if there are parallel portions of it, they won't have it, but the parts that are in series will. They'll have different voltages. I mean, unless you have two identical resistors, and they'll each have the same. But series resistors. So if I have a resistor equation circuit, which is all we're going to work with this week, then everything in series follows that. You just sum the resistors together. Parallel. Same voltage, different currents. Again, if you had two identical resistors, they'd actually end up with the same current. But otherwise, they're different. And then I have my parallel resistors equation. So we take everything we already know about series circuits and everything we know about parallel circuits, and we just apply that to the portion of a circuit that is series or parallel. So I think the best way to, well, I think before we do that, let's just draw some circuits and talk about what's series and what's parallel in those circuits. So actually, let's do this. What kind of circuit is that?
Series.
That's just a series circuit. There will be one current through everything. All the voltages will sum to zero, or all the voltages across resistors will sum to the battery, whichever way you want to think of it, it's the same thing. So that one is series parallel. Take a look, starting at my battery. There will be a current that flows out through this resistor. So this resistor is in series with that battery. All the current that flows out flows into the battery. Or all the current that flows out of the battery flows into the resistor. It's the right way around. But these two resistors are in parallel, right? My current's going to come up here, and then it's going to split. Some of it's going to go here, some of it's going to go here. So these two resistors are parallel. That means they'll have exactly the same voltage. They'll have different currents, assuming they're different resistor values. So I need to work this by recognizing this is parallel. And what I'll end up doing is using my parallel resistors to reduce those two resistors down to a single equivalent resistor. And then I can solve it as a series circuit. It's a legitimate schematic. It's a little non-standard, but is that series parallel, series parallel? Yeah, it's parallel. Everything up here is connected. Everything's down here is connected. So it doesn't really matter. I can just grab this and just stretch it out so it looks parallel. So we're going to have the same voltage. So again, series parallel. This resistor is in parallel with this. So it will have exactly the same voltage across that resistor as its battery. These two resistors are in series with each other though. So if my current came up from here, I would have a current that goes here that would be based on Ohm's law. I could just take this voltage, because it would be across that resistor also, divide that resistor and find that current. But I'll have another current that goes through here. So I have two parallel portions where these two resistors are in series in that one. If I were to come measure my voltage, I could measure from here to here. That's going to be essentially the positive to the negative end of my battery, and I would get this battery voltage, which would also be the voltage across that resistor, which would also be the voltage across those two resistors combined. So if I want to solve this, I'll take these two resistors as series resistors, combine them, replace them with a single resistor, and I'll have a parallel circuit I can solve. Okay. Let's go. Do you want to solve? Are you ready to try one with numbers, or ready for that? Let's try one. This style circuit's what I usually start with, so we'll do that. This week's homework is mostly just solving circuits like these, just going through and learning to solve these. And this week's lab, I believe you're building 3 circuits. And like many of our labs, the idea is you solve all the circuits first, so you can go home and do it, or you can work it afterwards here. And then you build them and make sure your measured values equal your solution values. So we should be able to solve them by hand and then build them and get the same values within a small margin of error. All right, so give ourselves a 15-volt battery. Resistor R1, and we'll make this 820 ohm resistor. Resistor R2, I'll make a 1 kilo ohm resistor. Resistor R3, 1.8 kilo ohm resistor. So I'll fill out my table where I want to find the battery voltage, the voltage across R1, the voltage across R2, the voltage across R3. So find voltage, current, and we'll go find power for all of them. Now I'm not going to be able to just add my resistor voltages together and have them equal the battery, because these two are the same voltage. So this voltage plus this should be 15 volts. But I can't add this plus this plus this. However, my power should all sum. It's conservation of energy thing. So all the power I'm putting into the battery should equal the power I'm taking out from the resistors. Do my solution. So that's the state I may have some English written around it. Hey, solve this voltage current. Okay. So I ask you, where would you want to start on this? Any ideas? Want me to do it?
Then the parallel part.
Yeah. As a general rule, take the part that's furthest away from the battery and solve it first. So I can't solve for voltage or current, but what I can do is I can draw an equivalent circuit. So I'm going to find R2, R3. It's not 23, it's combining 2 and 3. The equivalent resistance to R2 and R3. So how do I do that? Well, I use my parallel resistor equation because they're in parallel. So 1 over R23 equals 1 over R2 plus 1 over R3. So R2 is 1 kilo ohm. R3 is 1.8 kilo ohms. I do not need to convert them to ohms. As long as they're all in kilo ohms, I can solve it. I can get kilo ohms. If they're all in ohms, I can solve it. Okay. First one's easy. 1 over 1 is 1. Second one, 1 over 1.8 is 0.5555, all the way out, around up 6. So if I add those, let's say 1.5556. If I want to put my units down, just note that's kilo ohms. It's in the denominator, so it's kilo ohms to minus 1 power. Which is to remind me, the equivalent resistance is not 1.55 kilo ohms. It's 1 over that. So I'm done to get R23. I need to do 1 over 1.5556. I'll write that kilo ohms in there. A lot of times when you're actually solving this, it's easier not to bother putting in the units while you're doing all this, but you need to keep track of them. So I end up with 0.643 kilo ohms, or 643 ohms. Stop and do common sense check. Is it's got to be less than these, right? I got 2 paths for the current to flow, so my total resistance for 2 resistors in parallel will be smaller than either individual resistor. So the smaller and the smallest. The other thing I can note is if I have 2 resistors in parallel, it will always be bigger than half. Because the very lowest it could be would be half the value, which is, if I had 2 1 kilo ohms right here, it'd be 500 ohms. If you have 3 resistors in parallel, it's 1/3 the smallest, 4 is 1/4, and so far. But that just gives me a bracket where I can look at it and go, okay, it's going to be somewhere in this range. Okay, everybody good with this? Now I'm going to redraw my circuit. 15-volt battery, 820 ohm resistor, 643 ohm resistor, and I'll call this again, this is R1, and remember this is R23. So there's no physical resistor that's R23. That's just the equivalent of those 2 resistors. 1 kilo ohm and 1.8 kilo ohms are standard resistors. 643 is not. At this point, I have a series circuit. So I can just solve it if you take a look. But I'll go ahead and, for this first one, take it down one more, because I can make this a single resistor. So R1, 2, 3, those 2 resistors are in series, so I can just sum it. So I end up with 1,463 ohms, or 1.463 kilo ohms. Right, I just added those together. Like I said, you wouldn't have to go to that last step, but whatever. So here's the way I do this. When you're doing it on your paper, I just use your standard pencil. But here, I'll switch colors just because I'm going backwards. So I'm not going to draw new circuits. I'm just going to take the circuits we just drew and go solve on them. So now that I'm at this point, I can find this current. So I'm going to call that the current Ohm's law, 15 volts, divided by 1,463 ohms. So get 0.0103 amps, 10.3 milliamps. You know, if you have problems getting there, make sure you're calculating with me. You're good. So this current is going to be the same here because it's still a series circuit. So that's my 10.3 milliamps. In fact, if I look all the way back, that is the current that's going to come out of the battery and go through R1. It'll just split to become two different currents, R2 and R3. I can find the voltage across R2, R3 by multiplying 10.3 milliamps times 643 ohms. So 10.3 times 0.643. So if I do that, my voltage is 6.62 volts. My voltage across R1, I can actually draw the polarity there too, is 10.3 milliamps times 820 ohms. Which is 8.45 volts. So if you check these, there's a little rounding error on the like third or fourth decimal place. That shows these two voltages are exactly equal to 15 volts.
Very good. Yes.
I already had a question.
What?
Because for my homework with the series circuit, does the
Let's do
the
this
volts,
afterwards.
the voltage from the other resistors need to be equivalent to 9 volts? Like if they were to be like a 9 volt or 15 volt.
Let's talk about that when we're not in the middle of our.
Alright, well, unless like you're on this here.
Oh, here. So these two voltages have to sum to be that voltage.
Yeah. So I guess what I'm trying to ask is like the voltage has to be equivalent to that 15.
These two should add to 15.
Okay, that's all.
Yep. I wrote down our stat. I get 15.07 if you add those up. So, and I wrote our rules over there. Everything in series, same current, different voltages, they have to sum to 0. If you got it. All right, now I can take those and transfer them over here. So if I take a look here, and like I said, again, you wouldn't have to do this if you're doing it on your own, but if I go through here, I have 10.3 milliamps. Right there, right, yeah, 10.3 milliamps. I have, what's my voltage here? I can give myself enough space to write. 8.45 volts. And my voltages across here are going to both be the same. This is a resistor that represents those two in parallel, 6.62 volts. I can stop now and fill out all the voltages. The battery's 15 volts. Voltage across R1, 8.45 volts. Voltage across R2, 6.62 volts. Voltage across R3, 6.62 volts. Those two resistors have exactly the same voltage because they're parallel. Current. My battery has 10.3 milliamps. That same current has to go through R1 because it's in series. I don't know those yet. I know I get there, right? Current 2, current 3. Current 2, Ohm's law, 6.62 volts over 1 kilo. 3.68 milliamps.
So I noticed R2 and 3, when you add their current up, it equals
Yep,
the other one. That's always how it is.
It has to be that way, right? I have 10.3 milliamps of flow into this. It's called a node. The current that flows into the node splits to become the two currents there. And then they come back together and produce this. So this current really is the same current that flows in this leg. Down here is nothing connected to it. Through the battery, through the resistor. Splits, those two are going to be exactly equal to that current. Come back together. That's actually a law. We'll write it out here in a second. Conservation current might be the way you can think of it. It's got a name. Power. Let's try power. Yeah, so do notice here, I can't just add these voltages up and get 15 volts. It's not going to work. The one in parallel. Now, if I add the parallel voltage where these are both the same in parallel plus this, that's 15. Yes, these two currents are going to equal that current. So everything in series has the same current. Everything in parallel has the same voltage. Now, multiply across. We're good just doing power by going voltage times current. So I have 15 times 10.3 is 154.5 milliwatts. 8.45 volts times 10.3, 87.0 milliwatts. 6.62 times 6. Hit the wrong key on my calculator. 6.62 times 3.68. So if you take 24.4 milliwatts plus 43.8 milliwatts plus 87 milliwatts, you get 155.2. It's in the rounding error. If I'd left the last digit out, it'd be closer. But power dissipated, doesn't matter if it's series parallel or series parallel, power dissipated ought to be exactly the power into the circuit. All right, I have solved the problem. Isn't that wonderful? We solved the problem.